of course, you're going to go to the field and do some borings, some investigation. You're going to get your sample, and then you send it to laboratory, or you're going to do it by yourself. That would I recommend for the start of your career in any case. So the importance of the standardized and consistent procedure in soil mechanic in order to establish a quality control cannot be emphasized. That sometimes can happen depending on which country you are in, depending on your laws and your standards and your legislation. But usually every country and every continent have a different kind of standards. They worked on it for 100 years. You have for the American, there's ISTM that we are mainly going focus on, and there's a British standard that's like there for hundreds of years, and you have European standards. You also have some Japan standards and some from Asia, but we are mostly going to cover the American standards. And I'll speak a little bit about what's different from the American standard to European standard, because I used to work in Europe my whole life, but I do work in an Australian company, so I have feel about American standards as well, and that's their differences. So the presentation is going to describe the proper procedure for the laboratory testing of soil to determine the physical properties, which are an integral part of design and construction of the structural foundation. Before learning how to perform the laboratory test of the soil, play a really important role in the geotechnical engineering profession. You'll see it's like this is just some really simple tests that you're going to do every time you're there. You're in lab, every time you send a sample, but they're really important ones, and there's a lot of correlation between mechanical parameters that you're going to use for your design, between mechanical and physical parameters. So the tests involved in this presentation are performed according to the relevant standards. So mainly going to be ISTM or American standard, and the British standard, and of course a European standard that's have a lot of influence now in Asia and some part of the Africa. So the first one that we're going to speak about is going to be the measurement of water content. This one sounds silly, but this one is one that you're going to do every time you send your sample to the laboratory for the soil. Sometimes going to do it for the rock as well, but for the soil it's really important test, especially for the clayly soil. So this method covers the measurements of the water content of soil, of course, by the measuring of the weight of the water removed by drying the sample of moist soil to reach solid particles. The water content is usually used to access the consistency of the soil, to establish the relationship between the volume and the weight of the soil integrants, solid, water, and air. If you remember last time we spoke about how soil is forming, and that soils actually have three phases. One phase is solid particles, one phase is water, and one phase is air. It's usually air or another gas. That's usually air. This experiment is most important in the case of the clay, because the expansion of the shrinkage of the moisture content have a lot of the influence of the expansion and the shrinkage. So the water content may be defined as the let's move this. As the quantity of the water contained in soil. It is commonly known as the moisture content. However, the percent of the water content of the soil ratio is the rate of the weight of the free water present either on the soil surface or in the voids between soil particles to the weight of the dry solids of the soil. You'll see here we speak about free water. There's also another type there's two types of the water inside of the soil and the rocks. Usually with rock you can have water that is interrupted in the crystals. So using this method that water is not going to escape. It's going to stay there, because you're going to need to reach higher temperature to get rid of the crystalline water. As I already said, here you have here you have your solids at the laser. This is like usual how you can imagine the soil. You have solids that are basically soil that was formed from the rock in geological history. We spoke about soil formation before. I hope you were there. Of course, when you have soil, you have some void ratio and void between solids, and in that void there can be or water or air. So as I said earlier, that's a three-phase component of the soil. So basically, water content is basically how much of the water we have in our soil sample. For many soils, the water content may be extremely important index used for establishing the relationship between the way soil behaves and its properties. The consistency of the fine-grained soil largely depends on the water content. The water content is also used in expressing the phase relationship of the air, water, and solids as a given volume of the soil. This one standard is one that is used in the USA, also in some countries, countries on the western part of the world as well. Uh, it's basically it's basically like extremely similar to one we have in Europe. So usually the standards like all always or the same or like there's like just like baby differences. So what would you actually need to do this test is you have balance there. I just love to call it scale, just make more sense. That's the moisture can, that's spatula, and that's your drying oven. And of course gloves because that can get like pretty hot. So your scale needs to be like according to 1.1 0.01 gram. Your drying oven should be controlled at 105 to 110 degrees Celsius. You need to have metal container because you're going to put it inside of the dryer, spatula and gloves and the plastic slack. I wish I can show you the test like in real life so you can get like more feeling, but it is what it is. But I hope you're going to get idea how the soils is usually testing. So step-by-step procedures, like really simple test is the first what you're going to do is like record the moisture can and the lid number. So on every metal lid, you're going to have number because you're going to do like 20 moisture tests in one day. So you need to like connect that lid with with your sample that you're going to calculate later. Weight and record the mass of the can with the lid when it's empty and clean and dry it with the lid. So basically you're going to take your metal lid, you're going to write a number on your laboratory sheet that you're going to get or you're going to make. If you're going to work laboratories, so always going to be pre-made. You'll see like, oh, this is the what is the weight of my metal lid. I'm going to put a number there, just weight it like just metal. After that, you're going to place the sample of the moist soil in a moisture can and secure the lid. Wait and then record the mass of the moisture can containing the moist soil sample and the lid over it. So simple. You had your metal lid. You're going to your metal can with the lid. And after you're going to scale it and weight it, you're going to put your sample. Depending on the standard, you usually just put there like to 20 to 30 grams to 50. Not too much, but not too little because your accuracy of your calculation is going to depend on that. It's better to have more of the sample than less. I would say just uh, fill the lid, fill the can to the top, and you're going to be happy. After that, you're going to uh, put that your metal can and you're going to put it inside of the oven and you're going to leave it overnight. Uh, as we spoke before, the temperature of the oven is going to be between 105 and like you can have 210 or 100. It's fine. usually you need to do more than 100 because 100 is like boiling temperature of the water. If you want water to evaporate, you need to get there, right? This is where the European standard and American is be different. I would usually just leave it overnight, and you're going to be happy after it. But if you have like really moisty soil or organic soil, sometimes it is needed to have it more than 16 hours. I usually do 24, but when I did my master thesis, I did my master thesis on soil mechanic. I used to left it there for like 4 hours just to be safe. But that's not something that you're going to do in your laboratory if you're not making like any research, because like every time you do it's like, oh, it needs to be as fast as possible because you have other samples, you have your deadlines, and you're going to leave it like just like 16 hours, you will be fine. After that, you're going to remove the moisture can with your gloves because it's going to be hot, and you're going to cool it on the room temperature. But important thing is like you're going to have lid over it because you don't want to get moisture from the air in your room, in your laboratory, back to the sample. That can happen sometimes. Usually in the laboratory you have different like glassy thing where you can just put the samples, and then they're not going to lose, they're not going to gain the moisture because this is the vacuum one. So you're going to, of course, wait it again and put your numbers in your laboratory sheet, empty it, and then you're going to repeat procedure for several times. Because in laboratory for the physical test, you're not going to do it just one time. So you're going to need to be sure that's like that those are really strict results. So you need to get those right. So usually I used to do 3 times for the moisture content, and like every time expect the Atterberg limits because they are like they need to do like 3 or 4 hours just like of the pure work. So just do the 3 samples and you're going to be fine, and you're going to get like average result from it, and that's going to be everything you want. So let's go next. Someone is running over my presentation. I'm not sure
I
why.
was wondering if that was you or somebody else.
No. That's just someone else's signature, which is fine.
Okay, you were able to clear the drawing, correct?
I should be
Yeah.
able. Oh, not really.
Oh, okay. Let me see if
Uh,
I can do it.
yeah, please do. Oh, yeah. Thank
There
you
we go.
very much. Yeah. So when you're going to get your sheet and then you're going to do your calculation, like really simple basic calculation, you don't need to have high level of the math for the calculating laboratory sheets. So you're going to have moisture can and lid number, as I told you yesterday, because you're going to have 20 of them. It's different. It's something probably from the USA, because usually we don't have Q1. It's just like plain number. You're going to need to have mass of the empty can in the grams. You, at least in Europe, you already do everything we're doing in grams, and this is from the American standard, so I can assume that you're doing the same thing for the laboratory testing. So you write down your number, your weight of the empty can, and then you're going to put soil inside. You're going to weight it again, as we told, and then you're going to dry it, and then put the number again, and that's basically all you need. So there's like really simple calculation that you're going to have. Oh, this is my dry sample, this is my wet sample. The ratio between those things is going to be your water content ratio. Multiplied by 100 because you want to get in percentage, because every time you have water content, you're going to write it down in percentage. And it's going to be, for this example, it's going to be 8.3. Usually for the clay, you would have, depending on where you are, you would have a bit high results. Uh, Almost every time I test the clay samples, I would get between 15 and 25. Just reading the chat, trying to figure out are there any questions so far. So the conclusion for this test is this experiment is an importance of the measuring water content present in soil, in particular for the clay soils, since it gives significant value in the case of the clayly soil, for instance, expansion or the swelling or shrinkage. High water content that can be, then you're going to expect like really high settlements and small voids between solid particles. So water, when the soil contains significant amount of the gypsum or the organic material, it is recommended to keep the temperature on the lower temperature between 60 and 80 for the longer period to avoid oxidation and the loss of the water of crystallization due to the burning of the organic matters, and thus this lead the varying of the weight of the solid particles. Because sometimes you have like that you, you're probably not going to work with this kind of example, but if you're going to have soil where you have gypsum or some really organic soil, just do it like that, just to be safe. And then you're going to move to the specific gravity according to your American standard. This test method covers the measurement of the specific gravity of the soil solids that can pass the number 1 sieve by the water pictometer. We're going to speak about hydrometer later, but we already spoke about specific gravity in previous lecture. Just we put there just some calculation, just how to get it. Now we're just going to speak how to do it in lab. When soil contains the particle larger than number 4 sieve, the test method described is in another standard and shall be used for the soil solids that are like a bit bigger than what we're going to do here. It's like a gravel and sand. So basically, depending on how big your grains are, you're going to just use different standard for the determination of the specific gravity. The most complicated one is sure for the clays, because everything that's going to be complicated in your life as a geotechnical engineer is going to be related to the clay. Soil solids for these test methods do not include solids which can be altered by those methods, contaminated with a substance that prohibit the use of those methods, or highly organic soil solids, such as the fibrous matter which flows in the water. So that's basically some really specific case scenarios that you're probably not going to deal with as like junior geotechnical engineer or junior laboratory technician. Or if you're going to deal with those, you're going to have some senior that's going to just tell you exactly what you're going to need. Before that, you're just going to follow basic rules that you get on university, or that you get like as a part of the training for the juniors. So the specific gravity of the soil is defined as the ratio of the unit water or density of a given soil solids to the unit weight or the density of the water. If you remember last time we spoke about this, this formula there, not complicated. You don't need to remember it. Just need to have it somewhere in your mind that it exists. It exists, and you're going to learn it over time. You don't bother by learning calculations. Like, don't put it in your brain just like that. Don't do hard on it. The procedure employs Archimedes principle, which is, if you remember for the physics class from your high school, body submerged in the water will displace a volume of the water equals to its own volume. And this sketch here is going to describe you really simple what that means. So you have pictometer, that's one glassy thing fancy in the laboratory. You're going to have your soil, and you're going to put your solid soil in the water, and of course that's going to increase the volume of the water, and all test is based on that to calculate how the volume is changing, and you're going to get your specific volume. So this is the common results that you're going to have when you're going to test it. Usually, it is safe to assume that's going to be 2.665. If you're not going to do the test, if you're going to do calculation, you can assume that, and it's probably going to be fine. Just in case that you're not going to have your own laboratory test, but sometimes you just can assume the results, and you will see the specific gravity for the density of the solids you have in the soil is almost every time equal to the unit weight of the rocks. Because it's like really simple reason, as we spoke before about that, soil came from the weathering of the rock, and of course, if you have like basically rock particles in your soil, that those solids needs to have same weight as the mother rock. So the specific gravity of the soil solid is used in calculation of the properties of the soil, such as void ratio and the degree of the saturation. Those two are really important when it comes to settling. So, and of course, the odometer test. We're going to speak a lot more about odometer tests. I did my master thesis on odometer tests. I used to dream about void ratio, and if you're going to do odometer test, if you're going to calculate settlements, please do in your laboratory test. Please do the specific gravity test in your laboratory. You cannot enter the calculations. You just cannot use it if you're not having the gravity of the soil solids. So the specific gravity of the soil solids is used to calculate the density of the soil, which is soil solids. As I said before, this is done by multiplying the specific gravity with the density of the water at the proper temperature. The term soil solids is typically assumed to mean naturally occurring mineral particles of soil, like particles that are not readily suitable in the water. So basically just plain soil that you have. Therefore, the specific gravity of the soil solids contain extraneous matter such as cement, lime, or anything like that are not part of this, and you're going just to deal with the real soil solids like real soil. This one standard, if you can find it somewhere, you can for sure buy it. And when you're going to start working, you're going to have it, like depending on where you're going to work, you're going to have your standards are going to not going to be ISTM or the European standards, not going to matter. It's basically the same. There's just one difference that I'm going to speak later. It is by pictometer. So the pictometer should be this. Let me get my laser point. So what you need for test is the pictometer. That's the glassy thing I spoke about before. A sieve, a number one sieve that is going to, it's basically the sieve that is going to separate the clay and silt from the sand and the gravel. If you remember before, we used to talk about the soil classification, and there's 4 types of the soil based on size of the grains. So you have clay, you have silt, you have sand, and you have gravel. And standards are just defining better what clay is, what silt is. Just be different, but that's the one that you're going to remember. Number 4 sieve for the American standard, or for the European standard is going to be 0.063 millimeters. There's one question, that is where is the lid? So lid is one that you're going to need for the water content, and that's where the European and American standard are a bit different. I'm just going to speak about step-by-step procedure how to actually get it, and then I will say what's the difference between the European and American one. So you're going to get your idea where lid is. So what you need is like Number 4C, vacuum pump that you're not going to need in Europe. Scale, sensitive. As before, it's like usual laboratory scale. You're going to have it in every laboratory, a funnel and a spoon. So basically, scale, spoon, funnel, pictometer, your soil, and your vacuum pump, and that's all. Not super fancy, but the presentation hates me. Not super fancy, but soil mechanics are usually like that if you're going to deal it in laboratory. And I do recommend you do it in laboratory because it's going to be super helpful for you in your future when it's come to the design. So you're going to dry it in the oven as you're going to do it for the water content. For the guy who asked where the lid is, there it is. You need to dry it first because that's the only way to crush it, because you cannot crush wet clay. So you're going to just shake it through the sieve, and then you're going to get your small particles of the clay, dry clay, in one of your porcelain. Uh, difference between between the European one and an American one, at least what I used to do when I was doing this test, because if you're going to deal it with clay, it's going to be like mostly clay, or it's going to be just a little bit of the sand. It's not going to be too scary. What I used to do is when I get the soil sample, I'm just going to dry it, and then I will aggregate it, and I wouldn't sieve it, but I do like American standard here more because it just makes more sense. So you're going to fill the pictometer with water to its capacity. So if you remember that glassy thing that I, uh, I spoke before about it, just fill the glassy fancy thing from the laboratory to be full, and then you're going to weight it on scale, and you're going to discharge the water from the pictometer and dry it. The drying part is super fun because you have compressed air and you should play with it. And if you have some of your teammates in lab, you're going to probably piss them off because you're going to put air in them as well. And you're going to dry your pictometer with the compressed air, and then you're going to place your soil sample that you saved before, in the pictometer and fill it partially with water to like half of the 3/4 of the pictometer. You're going to apply the partial vacuum to the constant of the pictometer for the 10 minutes to remove all the air that's entrapped. Then you're going to stop the vacuum and carefully remove the vacuum line from the pictometer. Fill the pictometer to its full capacity. Then clean the exterior surface of the pictometer with a clean dry cloth, and you're going to weight it again. This is the part where the European one is different from the American, at least the German one. Since I did my master's in Germany, so what I used to do is that we didn't have the vacuum one. We didn't use the vacuum one. What we did is you get same as here. You put your soil sample. Everything is same until the vacuum part. When you get it, when you get the water inside, you're going to actually boil the water in hot sand, and that boiling of the water is going to act same as the vacuum. The all air is going to come out from the pictometer, and you're going to of course dry the sample, the cold sample in cold water, and then you're going to weight it. It is it needs a bit more time. So I would say I know the reason why the American ones it is in this way, because it is just quicker, and I would tell it is the accuracy is the same. So that's the most important thing that you need to have in laboratory. But that's just one baby difference. So how do you calculate it? It's mass of the empty clean pictometer. It's just classic fancy thing from the lab. Just going to weight it, nothing serious. What you usually have is you're not going to weight it every time you have number on your pictometer, and the weight's not going to change over the time. And sure, and you're not going to weight every time. You're just going to, oh, this is the pictometer number 11, and you know the weight of the number 11. Just going to put it there. You also know what is the weight of number 11 when it's full with water, because volume is not changing. You're just going to put it there. So you're just going to cut some steps there, going to save things like 5 minutes, which sometimes can be important when you have like really close deadlines. And you're going to get your weight of your soil and mass of the mass. That was weird accent. Mass of the pictometer filled with water, that you usually know from before because every time is the same. And this one is different, of course. And mass of the pictometer containing soil and the water, and GS is specific gravity. So just do your simple calculation based on everything you have here, and you're going to get your specific gravity. Extremely simple. Conclusion: this experiment is very important since the specific gravity of the soil is used in the phase relationship of the air, water, and solids in a given soil volume. I would say it's more important because you're going to calculate void ratio on it, and your settlements is going to to have a lot of relationship with the specific gravity. The results in this experiment are convincing to extend science there lie with the expected range of the common values. That's just speaking about one we had here. It's like normal value that you're going to have your specific gravity is. I would say you can assume 2.665 and you're going to be fine most of the time if you're not going to do like settlement calculation. More accuracy can be achieved by increasing the diameter of the pictometer that's used. This is due to the decrease in the surface tension effects. I will go in the chat because I saw there's some maybe questions there. So just to see what's happening. Someone from Serbia is there. Hi, my neighbor. Write a short essay. Okay, that's for the students, not for me. And are you familiar with the soil sensors or IoT devices that can detect the quality of the soil health? Example, soil moisture on nutrient levels compared to traditional way of the testing soil samples. Yes, but that is more for the agriculture, and it is not as accurate as you want to have it in soil mechanics. So I know what you're talking about. It's like a sensor that you're going to have in your soil for if you're growing some things, some stuff. I do have it personally for the growing of the vegetables, but for the soil mechanic, you cannot do something that is not standardized, and it is not as accurate as you want to be for the soil mechanic. So because there's a lot of calculation depending of the water content, and there's a lot of the relationship between the mechanical properties and the water content properties. So I would say that is better to use. I mean, if you're going to follow the law, if you're going to follow the standard, that's the one that you're going to use. And if something's happened, that's going to be on you if you didn't follow the standards. So it's basically it. But for the coarse grain sand, for the sands or the gravel, I would say that's fine to use. But for the clay, I wouldn't. I wouldn't, just because of the calculations and everything that you need water content for. You also need it for the void ratio calculation for the settlements. So it's pretty important standard, even if it sounds really simple and maybe stupid, and you're going to hate it if you're going to do it like 1,000 times. But it is one really important test. So the one next is a unit weight of the soil. So this one you're going to use like every time you're going to calculate something. Every time you're going to calculate something, especially in the soil mechanics, especially if you're going to deal with the landslides or the deep construction pits or even the foundations. So please just be aware of this one. This method covers the measurement of the unit weight of the soil specimen. The measurement of the soil bulk densities or the unit weight is difficult if there are gravel, stones, or the other materials present in the soil profile. Of the many methods in hand, the following experiment is going to describe the back-scold method, which is best suited for the samples which are not easily deformed or desiccated. A unit weight is usually determined in laboratory by measuring the weight and the volume of the relatively undisturbed soil sample obtained from the bus ring. Measuring the unit weight of the soil in the field might consist of a sand cone test, rubber balloon, or the nuclear densimeter. So basically, some things is going to be different if you're going to deal with the sand or the gravel, but with the clay, it's really simple, and you're mostly going to deal with probably with the clay because you don't have foundation problems in the rock, believe me. When it comes to definition, we spoke about this on lecture before as well. We just put there baby calculation. A unit weight of the soil mass is defined as the ratio of the total weight of the soil to the total volume of the soil. So it sounds pretty simple, and it is really simple. It's also known as the bulk density. However, there are some definitions that laboratory technician needs to know. There are porosity and the void ratio that are different stuff and that you're going to use in your future. A porosity of the soil is defined as the ratio of the volume of the solid contained in the weight of the given soil mass to the total volume of the soil, where the void ratio of the soil defined as the ratio of voids volume entrapped between soil grains to the volume of the solid soils. Sounds complicated. If you're going to read it once or twice, you're going to get it. Or when you're going to see how the formula is looking, it's going to be super simple. Let's get back. Unit weight is important in the case of the weight-volume relationship, such as the porosity, void ratio, etc. Unit weight is an important soil characteristic which affects many biological and physical processes, such as root presence in the water inflation. For everyone that is from the agriculture world, that one is important for you. Dry density, as defined as density of the soil or rock, and bulk density by soil scientists can be used to convert the water fraction of the soil from the mass basis to the volume basis and vice versa. When particle density, that is specific gravity, is also known, dry density can be used to calculate porosity and the void ratio. Sounds complicated. When it comes to porosity and void ratio, I know when you just look over it like this, it looks awful. But when you're going to see the formula, it's going to be super simple. You're just going to put 3 or 4 values there, and you're going to get everything. But it is important to understand what it means. So dry density measurements are also useful for the determination of the soil degree compaction. As we spoke before in the previous lecture, since moisture content is variable, moist soil density provides a little useful information expected to estimate the weight of the soil per unit volume. This is really important when you're going to build dams for the flood protection, because when you do like air dams, you're usually going to compact your soil, so it's going to be more impermeable. So basically, it's going to let less water through it. So that's the part that you're going to do like a unit weight more and more, and the moisture test more and more, and the compaction test more and more, because you want to see how is this changing when you do compaction of the soil for the air dams or something like that, or even for the road pavements. This one standards that you're probably going to use if you're going to work in USA, or if you're going to do it in Europe, is basically the same. This test is actually basically the same. So what you actually need is scale, as you're going to have in every laboratory, a paraffin wax that can be used for the sand, rocks, or the gravel, melting pan that you're going to use for the wax, of course, steel star cage, and a container for the can. So what's the step-by-step procedure? Secure a sample of the soil from the field where the soils is to be tested. This test differs from the previous test since its soil mass is bulk, not a dry soil. So that's the main difference, because you're going to here you're weighting the full soil with water inside and the air inside. You're not going to dry it, which means the moisture content is contains within the weight of the sample. Really simple. So that we need to dry it before for the soil solids, and for the unit one you're going to have it as it is in the nature. That's the reason why we're going to use this one more in your calculation than just soil solids. Trim a sample to the appropriate size by means of the straight edge, usually about rounded cube, about 70 millimeters in diameter. Specimen should be reasonably smooth and rounded, and you're going to weigh the sample prepared in the air, immerse the sample in the melted wax, and then weight it again while it's covered with the wax in the air. Submerge the sample covered with in the wax in the water, and then weight it in the water. Basically, that's more when you have sample that doesn't have like proper shape. Usually, what you're going to have is clay, and especially when you're going to do like odometer test, shear test on the soil, that you're going to have metal cone. You're going to put sample inside. You know volume of your cone, and just going to weight it, just plain metal, and write it down. You're going to put soil inside, because that's the way you're going to prepare sample for the odometer test or for the shear test. You're going to weight it again, and just going to divide everything there, and you're going to get your unit weight for the that works for the clay and a silt, and you're probably going to work most on it. So it's so super simple test. That's going to just be a calculation example of everything I spoke before. So as it was bulk mass of the soil sample, just pure soil, you're going to weight it, and the mass of the soil sample covered with the wax, you're just going to melt your wax, and you're going to put it over your sample, and then weight it again, and then you're going to put inside of the water, and then weight in the water. Sounds complicated. It's not. You're going to have a string that is connecting your sample and your scale. If you ever saw those Newton meter scale that is expanding with the weight, basically that, and density of the wax that is usually every time same, or you're going to have it from your technical specification, your laboratory that you're going to use. So the calculation is really simple, and the most important part is this one. This is the unit weight. This is the one. It is expression of kilonewtons in cubic meter, which basically means this is 2 tons, a bit more than 2 tons in 1 cubic meter of your soil sample. This one is really important one when it's come to calculations. The results is experimentalists convincing the expenses the obtaining such unit weight in the case the soil is heavy. That's true, because usually for the clay you're going to have around 18.5 or between 18 and 19. If you have more, you probably have a little different stuff in your soil, such as sand or the gravel. The box casting technique is effective of obtaining the measurement of the soil propensity in the loose and dry soils, where the other techniques are limited or ineffective. The box technique is also suitable for the obtaining pool density values at the micro locations with the soil profiles. You can do it on the field. This is important in applications such as evaluation of the effect of the soil layering on the water infiltration of the plant root penetration. That is important for everyone that's dealing with the agriculture. This experiment is very important since the unit weight of soil is used in the phase relationship of the air, water, and solids in a given volume of the soil. We already spoke about this fifth time in this presentation only, but it's you're going to see it's going to be super important when it comes to stress. I will speak about some mechanical, like really engineering part of soil mechanics, like mechanical part. We were going to speak about stress, about force, and if you have force on some area, it's stress. It's simple, but the stress is coming from the. There's some questions. Yeah. Is there a formula or formulas that can be used after doing soil profiles to determine how to reconstruct the soil mixtures to the optimal or acceptable levels? Mm, Not really simple one, but if you're asking for the soil compaction, like optimal one, uh, there is one thing. Every soil can be compacted at some maximum level of compaction. There is two tests. Uh, that one is like CBR, California bearing ratio, and one is Proctor test. Two different tests, and you're going to you usually do it at the same time, but the Proctor test is one that you're going uh, to use to get. There's one thing called optimum moisture content. So every soil you can compact every soil, right? But there is specific water content. When you get to that level of the water content ratio in your soil, or your compaction is easiest and maximum. CBR is going to define what's the maximum compaction. So basically, you're going to do CBR and the Proctor test. We're going to speak about those tests as well as the physical ones. Probably later because I think we are on the end of the class. This class, so it's probably going to be next lecture or the lecture after that one. Those two tests you're going to need, and that's going to have okay. The optimum water content ratio is 12%. So, and you know that you have 7, for example, because you have dry soil. And what you're going to do is like you're going to add on the field. I'm speaking about construction site. You're going to add more water to the soil to the moment you're going to calculate how much water you need for some volume of the soil, and you're going to get your optimal water content ratio. As I said, for example, 12. Just going to put water on the construction site, and you're going to get to the 12, and then you're going to start compaction. And from the other test, you're going to see that your maximum compaction is going to be 50% of of the of one that you have already, and that's when it comes to take in account your unit weight of the soil. Once I did the dam that was like floating float dam that's supposed to do to like float safe dam, and we did compaction of the soil, and we have like unit weight of the 18.5, and based on the CBR and the Proctor test, we got that we can get maximum of the 2.4 unit 2.4 or 20.4 kilonewton per meter cube, and that's going to be maximum that you can get there. It's usually important to remember. It's usually harder to do compaction on the plastic soil than on the elastic ones. And we're going to speak about Atterberg limits. We spoke about that before. If you remember Atterberg limits and the soil phases, you have a plastic limit. And if your plastic limit is higher than 30 or 50, in worst case scenario, that's going to be super hard to do compaction on that soil. So that's the reason why you're going to need CBR, Proctor, those tests like water content, because you're going to change it, unit weight, because you're going to change it because it's going to be different, and I forgot what I want to tell. And then you're going to have on your side, you're going to calculate everything based on your laboratory data, and you're going to do that's something called quality control and quality assurance. On site, you're going to take samples after construction, and you're going to do same laboratory test, and you're going to sorry, I'm reading the questions, so I'm kind of losing my conversations. I'm just going to get back to the questions because I assumed that I did reply to a question. The reason why I asked, my company does the road installment after water pipeline is replaced and days after the roadway collapsed. Okay, that sounds serious. That sounds serious. So usually when you do the pipeline, you have some kinds of the embankment a space for the pipeline. So you dig your trench for the pipeline to some depth, for example, 1 meter, and you're going to put your pipes on like 0.8 meter. On those 20 centimeters of the soil, you're going to do aggregate, like really fine soils and aggregate compaction. And there's going to be in project is going to be defined modulus of elasticity of that embankment. For the pipes, it is 30 megapascals of the dynamic one. So there is one test, one dynamical test with one weight on the, it's like 1 meter high and 3-4 weight. Based on that, you're going to calculate your modulus of the formation of elasticity. And since you don't want your settlements to happen as you had there, you have, those are design requirements. You have that you need to reach 30 megapascals of the embankment compaction before you put your pipeline. So you go there, put your aggregate, do your compaction in like in any way you want. It's what's easier for you. You do dynamic test and you see, okay, this 30 megapascals, I reach design requirements. Now I can put pipelines. After you put your pipeline, you're going to cover it with the aggregate sphere or the soil, but modulus of that field there cannot be less than you have before on the site. So that's the basically reason where your company may do wrong. So just go back, see did you met design requirements for the subgrade of the pipeline, and what was procedure of the filling back the trench. Is there any more question? How can I determine what soil I have in my garden? Good morning, Dr. Jean, if I got it right. Uh, depend Depends what you want. The this moment we're speaking about soil mechanics. That's what you need for if you're going to build something else. If you're asking for the agriculture, uh, I'm wrong guy to ask. But usually you would take sample and send to the laboratory, uh, depending on what you want. If you're asking for the agriculture, you're going to send your like sample that you made and put in a bag and just send to some kind of institute. If you're going to if you're asking for the how do you know can you build something there, then there I can answer to you. So usual procedure is to do or the excavation pits to like 2 meters depth, depending if where you're in the world and what kind of soil you're expecting and what you're going to build. Or what you would do normally is do the drilling of the borehole with the continuous sampling. Depends on what kind of construction you want there. Uh, your depth of your borehole is going to depend on type of the construction, type of the expected foundations, and on your budget, of course. And then you're going to send all those samples to the laboratory with help of the geotechnical engineer, and then someone is going to do determination of the mechanical properties and the physical properties of the soil. And based on log of your borehole, they are going to, in the report, they're going to tell you what kind of foundation do you need for your building, where to put foundations, and what are the mechanical properties, and what's going to be settlement of your foundation and needs to be in some design parts. We're going to speak about mechanical properties of the soil. We are going to speak about design of the foundations according to Eurocode, and we are going to do some kind of modeling, but it is going to take some time. Before that, we are going to speak more about laboratory tests. Then we are going to move to the field test that you're asking there, how to actually do the field test, how to actually do the logging of the borehole, how it looks like, how to get water from the soil, how to get water from the underground, how to design wells eventually, if you want, and those kind of stuff. And then you're going to speak about the mechanical properties of the soil, mechanical properties of the rock. You're going to learn what the stress is, what the strain is, uh, how the stress behave on excavation. And then after that, we are going to speak how to actually design stuff. So I think that's going to be all. It's already 1 minute past the time. So I hope if you're going to have a more questions, just raise your hand. This is the time.
I don't see any other questions, but I have a quick question.
Yep. Tell me.
When I used to do construction and we were laying the foundation for a house or for the
Okay.
flooring, we would have this compacting machine that would compact the soil, but we'd have to lay down some water every inch or so. Now, what is the purpose of that water?
Yes. So if you're going to do usually when you're expecting that you're going to have compaction of the soil for the foundations, you're going to do Proctor test. And that's one test is specified to define that's called the optimal water content for the compaction, because soil is going to compact differently based on the water content ratio. So every kind of the soil, depending where it is, have different optimum water content ratio. So for example, it can be 12%. And that number means that your compaction is going to be best on that water content ratio. So what you do on site, you get lab data, and what you're going to have on site is basically that. You're going to put one layer of the soil, and then you're going to put water in it. You're going to calculate how much water you need to reach, from example, from 5 to 12. And then you're going to do compaction, and that compaction is going to be best based on your lab results and based on your optimum water content for the compaction.
Yeah, we used to put the water in and then feel the soil with our hands, kind of compact it with our hands,
Yeah,
and then get a sense of if it was holding its form, then it had enough water. Is that that's not a proper way, but what do you think?
yeah. You basically did the Atterberg limit test. You didn't know about that. So usually, like if it is clayey soil or silty soil, it's like really fine grained soil, or even the sand. When you put water inside of your sample, the properties of your sample of your soil is going to change. So there is some status of the soil that you have. You have solid one, you have semi-plastic, you have plastic, and you have liquid one. So of course, if it's super dry, it acts as a rock. So that's like just pure solid. But if you're going to increase water, the soil is going to start behave like completely plastic. And depending of how much of water you have in the soil, the mechanical property is going to change and the behavior of the soil is going to change. At the moment, you can add too much water and then it's going to start acting just like water. And then that's not what you want. So depending of how much water you have in sample is going to you're going to have different kinds of the behavior of the soil. It usually work best for the clay, but also if you're going to like do like proper compaction, you're going to have some sand there, some gravel there, because it's easier. You need a bit less water, and then you're going to do your proctor test, optimum water content, put the water inside, compact it, and that's it. But yeah, like uh, if you have beach somewhere around you or riverbed, something like that, and you have sand there, and when you put just dry sand, you try to build castle with dry sand, it's not going to work. But if you're going to put a little bit of water inside of your sand, you can build whatever you want. That's something that's called like it's not cohesion, but it's acts like cohesion. So it's like basically fake cohesion. So because soil, the water have pores that can hold soil particles together. So when you just put a little bit of water in your sand, you're going to have your effective cohesion is going to act like cohesion. So you can build whatever you want. Same with the compaction. Depending of how much water you have in your soil, if you're going to have right amount, it's going to be super easy to compact the soil. Like in any any method you can use, just walk over it, it's going to compact.
I do see a hand raised. Do you have time for another question?
Yeah, sure. I have one more in the chat as well. I'm going
Okay.
to get that one. A quick question: what are some contributing factors to the sinkholes other than weight? Oh, the sinkholes. Oh, that's the one complicated question. The sinkholes. The sinkholes depends on the liquefaction of the soil. Uh, that sounds complicated, but basically, uh, it's usually happen when you have layered soil, and at one part of the soil you have bit grainy soil, such as sand. It's usually sand, and you have water inside. Usually, you have water everywhere in underground, and it's all so depending of the water content in your sand and how much sand you have there, how much water you have there. Sometimes, especially with the earthquakes, it the sand start acting same as water, so it doesn't have any mechanical properties. It is basically same as water. So what happened there? Your layer that used to hold something before just became like completely useless. So if your layer is like 1 meter, 2 meters, and you're really shallow, or you're really near to the surface, and your 1 meter layer start acting like nothing, you're going to have collapse just because your layer of bearing soil lost any kind of mechanical properties. That's usually happening with the earthquakes because with the earthquake, the grain distribution with the water just change, redirect, or for it's not taking like hours or something like that. It can take like just 3 minutes for the earthquake that you don't have bearing capacity of your layer of the soil. It's enough for the sinkhole to form or to start forming. Just a comment, we have been having the earthquakes in the Caribbean in recent times, and I noted the foundation is changing. Yes, there is one part of the geotechnical engineering or the structural engineering that is just for the construction of the foundations for the earthquake areas. Usually when you do the geotechnical report in the European Union, or you're using the Eurocode, we have Eurocode 8 that is basically just for the earthquakes. You're going to have one parameter that is accelerator, the soil accelerator, basically like that. It's like defining how fast the waves are are moving through the soil or the rock. So based on that parameter, you're going to design foundations. It's depending on the country. Every country in the European Union, or basically in Europe, have already maps that have predefined accelerators. So you're just going to get data from the map. It is based on the geophysical investigation site, and in Europe, you just have those data prepared. If you don't have those data prepared, you're going to have the geophysics that's going to record velocity of the wave through the soil to get those data, and it is also depends on the place where you had central parts of the earthquake before. So of course, some parts, depending on the tectonics, some parts are more dangerous than others. So you have magnitude, expecting magnitude of the earthquake, and you're going to use that one, acceleration, and you're going to design foundation based on that. It's more structural engineering than foundation engineering, but it's really important. This is a really important topic for me. Request your email address for the further consultation on the testing on the soil mechanics. My email address is that. Okay, I get it. I saw two raised hands, so please enlighten me with your questions.
Richard, are you able to? There you go.
Yeah. Okay, I have a question. This subject is very interesting for me because we have found some difficulties to measure the compaction of the sand because we are building the ring wall, and we have to fill in with the sand, but that sand is the river sand. But how to we can't make proctor test to measure the compaction, because we have to, when we fill in 30 centimeters, we have to test the compaction. But how to test that compaction? I'd like to test the compaction. That is my question. With the sand without cohesion. Yeah.
So, okay, thank you for the question. So basically, you have in situ test of the modulus of the elasticity. When you do compaction of the soil, you usually try to get a modulus of the elasticity of soil. you have you have two different kinds. One is the dynamical one, and one is a static one. What you usually have on site for the quality control and quality assurance is like it's mostly dynamical one, and European standards would say that you do one dynamical test on every 10 meters and one statical on every 100 meters of your road or your wall or whatever you're building. So in your design, you should have specify a subgrade coefficient and the modulus of the elasticity that is needed to be reached. It's usually between 30 and 60 megapascals for the pipes for the most of the roads. It is 30 megapascals, and for some more complex stuff, if you're going to change the soil for your foundation, is going to be more close to the 60, and basically go there, or you're going to hire someone to go there that have a device. It's a really simple one. It's a cheap one. It's basically you have plate weight, and you have your soil there. Just put it there. The plate weight is going to fall with the free fall from 1 meter, and you're going to have recordings of the settlements of your soil or whatever you have there, based on kinematic energy of that plate. So from that, you're going to have software. It usually came with software. Everyone that have device have software. You're going to get your modulus of elasticity, and if it's less than 30, it's probably something wrong there. You need to have more of the compaction of the soil.
Okay.
So I hope I answered your question. There's
All right.
one.
Oh, okay. Yeah.
There's one more raised. If you can pass the question.
Okay, thank you, Dr. Lampard, and I have not seen the name of the presenter. Thank you for giving me the opportunity. I'm happy
Did you see
to.
Safet Mutapcija?
Yeah.
Oh,
That.
okay.
Okay.
Thank you, Lampard. So I'm also interested in the question George mentioned. But regarding what Dr. Lampard mentioned about putting water into the soil, I understand. I also have question in that aspect too, because I understand that has to help in settlement, soil settlement, so that before the load comes on it, because since if it is not well settled, the load now will compact it. Since the load is rigid, that may lead to cracking. That is movement that is not well controlled. So it has to be controlled before the load is put on top, so that it will not cause the uncontrolled movement, which may not be evenly, and some parts goes down while some are still floating. Then it will be cracking. But now, how will one determine the right quantity apply in order to compact it or make it settle the soil before the load comes in?
Okay, thank you for the question. So basically, as I said for the question before, on every site you have quality control and quality assurance tests. So for every construction site you will have quality control. Usually, like from what I saw from the construction sites before, like every time you have construction site, you have like bunch of trucks there, and usually those trucks are more than enough to get your compaction. At this moment, I'm working. We have like huge embankment. It's like 45 meters in height, and we always have trucks there. So our design requirement was 30 megapascals of the modulus, and we got more than 100 just because we had trucks all over it. So it is not, you cannot overcompact it. That's basically impossible, because everything that is above design compaction, it's good, it's better to have more compaction than less. So you're not usually calculating how much of the your weight you need to put on soil for the compaction. It usually happens just on the construction site, just with the trucks and everything around. That can happen if you have like really soft soil, but you usually are not going to compact it. You're going to mix it in cement or some other some different techniques to actually get strength. So, or we're going to have like huge dynamic compacting machines, as you maybe saw somewhere on YouTube. But that's the reason why you have quality control on site. That's the reason why it's defined by the standards. That's the reason why you're doing the dynamical tests and statical test of the models of the elasticity, just to know, are you over design requirements? So when you get on design requirements, you can do whatever you want. It is controlled. Before you put load on that soil, first you're going to know that you're above design requirements. Of course, you have water there. The water is your enemy when it comes to settlements, but also before you're going to put load, you're going to have drainage as well. So that water is going to go somewhere else, and it is not going to affect your settlements. When we are speaking about settlements depending on water, that is different from the compaction, because if you're going to lay foundations on pure clay, that happens occasionally when you got your mechanical parameters of your clay. And like my hometown is basically built on a clay beds, and it works. We don't have much settlements. All the buildings are still there, just because we have like perfectly designed foundations for that kind of soil. Usually what happens with settlements, you have water inside of the soil. With the settlement, that water is going to go somewhere else. That's the reason you do drainage, but don't confuse compaction and settlements. It's like two different terms. We are going to speak a lot more about settlements. But that's more for the mechanical part of the, like one really engineering part of the lectures, going to come a bit after we understand some basics.
Thank you so much for your explanation.
No
I think
problem.
I have to look into that topic again. Thank you.
I'm glad. Thank you. Is there more question?
I think that's going to do it, Safet. We appreciate your time to come and talk to us about this. You're basically just scratching the surface of the soil issue. That's a joke, actually.
There's years of work for that.
But there's so much to be done on this, because it's so important to get the soil correct when you're building something. If it's your building is going to fall down, or it's going to move or crack.
Oh, that's true. That's true. Oh, if you're going to look over the first presentation, was just, oh, this collapsed for that reason. This collapsed for that reason. So the first presentation was just how everything's collapsed because of poor geotechnical engineering. So we started on that like bad designs.
And now you're getting down to actually doing the testing to figure out which type of soil will work for you and which type won't.
Yeah, so basically we are from the collapsing, oh, please don't do that, because we are going to do it in how it's supposed to be. We are going to cover the basics, and from the basics, we are going to build to the design part, and then you need to understand basics before the building something, right?
So now where do you go from here? What are you going to talk about next?
We are going to cover the laboratory test for the physical parameters. We're going to speak about Atterberg limits and some stuff like that. We're going to speak about field investigations because on the field you get your initial samples. You're going to speak about some like maybe some real life project I had before. Field investigation. From the field investigation, we are going to move to the actual mechanics. We are going to speak about stress, about strain, about how the stress is forming with excavations, and then we are going to speak more about mechanical tests because we need to understand stress before we move to the mechanical testing. We are going to speak a lot about odometer testing. We are going to speak about shear testings and maybe triaxial testings. That one can be a bit complicated, especially for the just theory. If you cannot see it how it's working, because those are tests that you're going to get your main parameters for designs from. So and then from that point, after we describe everything related to the mechanics, like simple mechanics, we are going to move to the actually how design stuff, how design really simple foundations from the home or something like that, following some standards. And then we can move from more complex stuff. We can move from deep excavations. We can move to the tunnels. I actually work most of the tunnels now. I do designs for the tunnels, so that can be one lecture, how to use the finite element softwares based on the parameters. But first, we need to cover like some foundations related to the how this basically on stress.